Hello and welcome to our lesson on cofunctions and sum or difference identities. So what we're going to look at today are some new identities to add to our toolbox. So far we've seen the fundamental identities and how we can use those to simplify expressions as well as verify new forms or alternative forms of our identities. The identities we're going to look at today can be used in the same processes, but they can also be used to do some evaluating in new situations, and then ultimately all of these identities are going to be useful in solving. So let's start with talking about cofunction identities. Now, in order to understand these cofunction identities, which are in this big box here, it's really helpful to talk about the graphs of our functions first. So I'm going to start with the sine wave and its cofunction, which is the cosine wave. So let me look here for a second. If we look at the sine wave, hopefully it's easy to see the connection between the sine wave and the cosine wave, which I just populated there in green, in terms of transformations. There are a couple different ways that we can get from the sine wave to the cosine wave in terms of transformations. For example, if I took the sine wave and I just shifted it over pi over 2 radians or 90 degrees, let's say to the left, so maybe I just add pi over 2, then look at that. The sine wave is now directly on top of the cosine wave. Those two are exactly the same. So that's a transformation I could apply to get from sine to cosine or vice versa every single time. Now, the transformations we're going to look at are going to be transformations that I can apply to any function and what we call its cofunction to get the two to map onto each other every single time. So another way we can transform this graph, let's start with sine and cosine, is to first reflect it over the y-axis. And we haven't talked about this one, but if I multiply my function by a negative, it reflects it over the x-axis. Let me get rid of this for a second. So that negative there reflects it over the x-axis. If I want to reflect over the y-axis, I would multiply x by a negative. So if I take sine, reflect it over the y-axis, and then shift it, again, pi over 2, or 90 degrees, then again it looks exactly like my cosine. So if I put cosine in the picture, same exact graph. Okay? Now, that set of transformations will apply to every function and what we call its cofunction. So let's go over here to tangent, for example. Here's what our tangent function looks like. If I take tangent, reflect it over the y-axis, and translate it pi over 2 radians, or 90 degrees, then now it looks exactly like cotangent. So I can put cotangent, or that transformation of tangent. Those two graphs will look the same. So those two are going to be referred to as cofunctions of one another as well. And then the same thing for secant and cosecant. So here's what our secant graph looks like. Here's what our cosecant graph looks like. Okay? If I take my secant graph, reflect it over the y-axis, and then shift it over pi over 2 radians, it maps exactly onto the cosecant graph. So, I gotta sneeze. I'm so sorry. In terms of transformations, we can say the sine wave is just a transformation of the cosine wave, and there are many different transformations that we can make to get from one to the other, but and this vice versa as well. But one graph can be obtained in one way by reflecting over the y-axis and then translating, which is just shifting, pi over 2 radians or 90 degrees left or right is going to be the same shift. And those two transformations will map a cofunction onto or map a function onto its cofunction every single time. So this connection always occurs between what we call cofunctions. So what we're going to say is that cosine and sine are cofunctions of one another. So sine and cosine are cofunctions. If I take sine and reflect it over the y-axis, translate 90 degrees or pi over 2 radians, I will end up with the cosine wave and vice versa. Also, another highlighter color here, cosecant and secant. Those are going to be cofunctions of one another. They're the same transformations. And then finally, cotangent and tangent, those are going to be cofunctions of one another. Cotangent, tangent. Okay, by graphically reflecting over the y-axis and translating pi over 2 radians, we can get one of those functions to map exactly onto the other. And these go in both directions, so these are really the same thing here, just depending on which direction you want to go. So all the boxes underneath the ones I highlighted are just the reverse direction. Now, because the angles that we're looking at, because we're seeing that 90-degree connection between where we start with our angle and how we translate over, right, that shift of 90 degrees. If we look at the angles here, so the theta that we have here and the 90 minus theta, again, that's just a translation, but if we were to add those two angles together, we're going to end up with that 90 degrees, okay? Angles that add up to 90 degrees have another name, and since we know that name is those are complementary angles, we can also state that the trig function of an angle is going to be equal to the cofunction of its complement. And that's really the way that wording, that's, I can't spell, complement. Not like you pay a compliment is an I in the middle there, but the complement of an angle is with an E in there. And this is not differ. This should be cofunctions, not differ by, but add to. Angles of the cofunctions adds 90 degrees, then we end up with this statement. Again, this is how I hold it in my head. We can say the trig function of an angle, so like the sine of an angle, is going to be equal to the cofunction of its complement. So the sine of an angle is equal to the cosine of its complement, which means subtract that angle from 90 and figure out what's left. Or the secant of an angle is equal to the cosecant of that complement. Or the cotangent of an angle is the cofunction, which is tangent of the complement of that angle. So then it allows us to evaluate situations like this. So, for example, in number 1, if I wanted to find the cotangent of theta knowing that tangent is 25, this won't take a lot of work because cotangent and tangent are cofunctions. If they are cofunctions, then the tangent of this angle will be equal to the cotangent of the complement. So what I'm looking for, theta there, should be the complement of 25. So theta is just going to be 90 degrees minus the 25 degrees, which means that missing angle is going to be 65 degrees. So again, the tangent of our angle is going to equal the cotangent of its complement. Okay, same thing for number 2. Sine and cosine are cofunctions. So the cosine of my angle here has to equal the sine of its complement here. So if I want to find the complement on this one, again, I'm going to take what I have away from 90. So 90 minus, in this case, a negative 30 means, I should be putting degrees here, that the angle we're looking for on this one is 120 degrees. Or here, again, if I'm taking the cosecant of an angle, it's going to equal the secant of its complement because cosecant and secant are cofunctions. So I'm going to, again, find my angle by taking the complement, or finding the complement to pi over 8. So the other two I subtracted from 90, but remember 90 degrees is pi over 2 radians, so it kind of depends on what we're working with here. If we're working in degrees, subtract from 90. If we're working in radians, let's subtract from pi over 2. So maybe you want to make a note to yourself somewhere, right? Pi over 2 radians is equal to 90 degrees. So here we're going to go pi over 2 and subtract the pi over 8. Which means I need a common denominator. Not too bad. If I multiply my first fraction by 4 over 4, then I'm really trying to subtract 1 over 8 from, or 1 pi over 8 from 4 pi over 8. And 4 minus the 1 is going to leave me with 3. So the angle I'm looking for here is going to be 3 pi over 8. And if you wanted to use your calculator, the calculator could confirm any of this. So if you asked your calculator, for instance, for the cosecant of pi over 8, it's going to give you some decimal, and then you can find the secant for the angle and I used theta, but this one's called x. Let me fix that. This little variable discombobulation here. Did I do that in the last one too? No, that one has a theta in it. Okay, sorry. So x we're saying is going to be 3 pi over 8. Let me plug that in. and I should get the same decimal, and I do. So you can use your calculator to verify your work if you need to. Okay? The thing is, we're trying to look for exact answers when that's possible, so we don't want to use the calculator to do the work, we want it to verify the work. Alright, so those are our cofunction identities. Again, hopefully they make sense based off the graphs. The next identities we're going to look at are not as easy to show you where they come from. So there are proofs for these if you're very interested in knowing where they come from and how these are derived. I would say Google proof for some difference identities. I'm not going to take the time here because I just don't think it's worthwhile. The proofs are complicated and very messy, but what we're going to look at with these sum or difference identities is a way to extend something we can already do with the unit circle. So when we're looking at the unit circle, remember we're trying to use this to quickly reference and find exact values for trig functions. So for example, if I said what is the cosine for pi over 6 radians, you go to pi over 6 and you find the x value that represents the cosine. Or if I said what's the sine for 120 degrees, you find 120 degrees, you go to the y value, and there's our sine, radical 3 over 2. So we can already use the unit circle to find the exact value for all 6 of our trig functions of the angles that appear explicitly on the unit circle. What the sum or difference identities are going to do is extend that ability to find exact values of our trig functions, but it's going to extend it to angles that aren't explicitly on the unit circle. So let me show you an example. Let's say that I wanted to find the exact value. Anytime we're looking for an exact value means we're not trying to get some decimal from the calculator, because you could easily put sine of 75 degrees in the calculator and get a decimal approximation. It's not what we're looking for here. I'm looking for an exact fractional value. Now I don't have 75-degree angle explicitly on the unit circle. However, 75 degrees can be rewritten as a sum of two angles that are on the unit circle. So when I'm looking at one second here. I lost my place. Okay, sorry. When I'm looking at 75 degrees, I can rewrite this as the sine of 45 degrees added to 30 degrees. So again, 75 is a sum of two angles that are on the unit circle. So if I can take my angle and rewrite it as a sum or difference, then I can apply one of my sum or difference identities. So in this case, I have the sine of a sum. A lot of page flipping is going to happen here. So let me write down my formula so I don't have to keep going back and forth. The formula for the sine of a sum says that the sine of the formula uses u and v is going to be equal to sine u cosine v plus cosine u sine of v. Okay, so there's the formula. If I know what u is and what v is, then it shouldn't be too hard to plug these things in. So instead of u and v in our problem, we have 45 and 30. So applying this formula to my problem, we're looking at the sine again of 45 and 30. So this will be the sine of 45 times the cosine of 30 plus the cosine of 45 multiplied by the sine of 30. And these should all be degrees. Okay, so let's simplify this. Because the sine of 45 and the cosine of 30, cosine of 45, sine of 30, these are all things I can get directly from the unit circle. So on the unit circle, let me try to fit all this in here. On the unit circle, our 30-degree angle intersects at, remember this is all in your left hand too, so if you're using the hand trick, the 30-degree angle intersects the unit circle at radical 3 over 2 and 1 over 2. And the 45-degree angle intersects the unit circle at radical 2 over 2 and radical 2 over 2. So I put the picture on the notes for you, but hopefully we're not needing that. So when I ask you for the sine of 45 degrees, I'm going to 45 degrees and picking out that y value. So that's going to be radical 2 over 2. when I'm asking you for the cosine of 30, I'm going to 30 degrees and picking out the x value. So that's going to be radical 3 over 2. Plus cosine for 45, that's going to be the x value there, which will be radical 2 over 2. Oops, one more highlight. Come on, pen. And then the sine for 30, oh, that's my eraser. Sine for 30, that's going to be right there, that y value at 30, so that's going to be a half. And now all that ugly stuff is gone. I just have some fractions to work with. So I'm going to multiply these two like it tells me to. When I multiply the top, radical 2 times radical 3 makes a radical 6. Multiplying straight across the bottom, 2 times 2 makes 4. Over here, straight across the top, radical 2 times 1 is radical 2. Straight across the bottom, again, we get 4. Since I have a common denominator, I can put these together, and that would be the exact value for the sine of 75. That was weird. Of 75 degrees. Okay, and again, your calculator could be used to confirm this. So in the calculator, if I put in the sine for 75 degrees, and let me go to degree mode, I get that decimal approximation. What I want to verify is that the fraction I have equates to the same decimal. So if I put in radical 6 plus a radical 2 and divide by 4, boom, 0.9659, whatever, all that ends up being exactly the same thing. So one way for you to verify your work. Again, if I asked you for the exact value for sine of 75, you're not just going to go into the calculator and give me that decimal. I want this exact form, but by all means use the calculator to verify that you did it correctly. Alright, so let's try that again. Kind of a lot going on there. Cosine of 105, and there's going to be multiple ways to do these. So it kind of is what's jumping out at you. You're trying to find a way to rewrite the 105 in terms of angles that are on the unit circle. So maybe we can look at the unit circle. And I apologize for my sniffles. My goodness. Okay, so on the unit circle, I'm trying to get 105 and a sum or difference, however it works out. So I'm right off the bat seeing a couple different ways. Like if I was to add 45 and 65, I can get to 105. Or if I was to take 150 and subtract out 45, then I can get to 105. So it's really whatever jumps out at you first. Either way is going to be totally fine. So maybe we use the sum. I think that probably would have been a little bit more obvious. If I can rewrite that 105 as 45 plus 60, then I can apply my sum, cosine of a sum identity. So back here, I'm going to rewrite this. Instead of the cosine of 105, it becomes the cosine of 60 degrees plus 45 degrees. 60 and 45 still being 105. And now again, I want to apply my formula. The formula says the cosine of a sum, so we'll say u plus v, again that's what the formula is using, although whatever the variables doesn't really matter. It's going to be cosine u cosine v, and then we're going to flip the sign here. It'll be sine u sine v. So we have, once again, the cosine of 60 and 45. So this will be cosine 60 cosine 45 minus sine 60 sine 45. And so now I need to know what those things are, which again comes right from the unit circle, but I'm going to try to do this without using that reference. So a 60-degree angle, again, it's all in your left hand if you're using the hand trick. It's going to intersect the unit circle at 1/2 and radical 3 over 2. And then 45, we just did that one. That's right in the middle at radical 2 over 2 and radical 2 over 2. So now I have everything I need to finish evaluating here. So this is going to equal the cosine of 60. So cosine of 60 is going to be right here. That's a half. And then the cosine of 45. Cosine of 45 right there. That's going to be radical 2 over 2. And then we're going to subtract sine of 60. That's going to be here, radical 3 over 2. And then the sine of 45, oh my goodness, sine of 45, that's right there, radical 2 over 2. And so very similar to what just happened. We have a radical 2 over 4 here. This time we're going to subtract a radical 6 over 4. So the final simplified form will be a radical 2 minus radical 6 over 4. So this one was for the exact value of the cosine of 105 degrees. So even though 105 degrees wasn't explicitly on the unit circle, I could still use the unit circle to find that exact value using my identity. Now, there are definitely some connections in the answers that we see here. A lot of the answers are going to end up being very similar because all of the coordinates on the unit circle are similar, right? We're looking at radical 3 over 2's, 1 over 2's, and radical 2 over 2's. So there are only so many combinations of things we can do with those. So most of our answers are going to end up looking pretty similar. There's another format you'll see come up in the, I might come up in the next one too, on the homework. But again, use your calculator to verify, and a lot of the answers will look similar because the coordinates on the unit circle are all kind of looking similar. All right, so let's try the next one. The next one, we're looking for the tangent of pi over 12 radians. And we have, again, these identities for tangent, if I can make a tangent of a sum or tangent of a difference. I know pi over 12 isn't on my unit circle, but for me, it's just, I just can't think in radians in the same way I can with degrees. So I would probably just convert this. If I have pi over 12 radians and I want to make it degrees, remember I could multiply by 180 over pi. Oh no, pen, don't pen, just don't. Pi over 12, if I multiply by 180 over pi, then I can convert this. So those would cancel. 12 is going to go in there once, and in there, let's see, 1, and that would be 60, so 5. So this is going to be 15 degrees. So if I want, and you can do that with your calculator too if you haven't messed with that yet. If you took pi over 12 and multiplied by 180 over pi, then you can get that 15 degrees as well. So if I convert this, it makes it a little bit easier for me to work with. So this is the same as the tangent of 15 degrees. Now again, 15 degrees, not explicitly on my unit circle, but I can find some angles that can get me to 15 degrees when I add or subtract. I'm sorry for the scrolling. So 15 degrees, again, there's going to be a lot of ways you can do this. There's a difference of 15 degrees between a whole bunch of these angles. It doesn't matter what two you choose and whether you choose a sum or a difference. So I'm going to go with 45 and 30. If I could stay in quadrant 1 and deal with all positives, that would be my preference. So I'm going to call this tangent of 15. I'm going to, if my pen can work here, call this the tangent of 45 degrees minus 30 degrees. 45 minus 30 again being the same 15. Okay? So our formula, this is the tangent of a difference. So this formula says that the tangent of a difference, u minus v, is going to be equal to a fraction of the tangent of u minus the tangent of v, all divided by 1 plus tangent of u times tangent of v. So not the prettiest thing, but that's okay. We're going to plug in, let me change colors here. We're going to plug in 45, my gosh, 45 for u and 30 for v. So for our problem, we're going to say that the tangent of 45 minus 30 is going to be equal to tangent of 45 minus tangent of 30 divided by 1 plus tangent of 45 times the tangent of 30. Okay, so I need to know the tangent for my 45 and my 30s, but those values aren't explicitly on the unit circle, but I can still get the information from the unit circle. So 30 degrees, we just said a second ago, 30 degrees intersects the unit circle at radical 3 over 2 and 1 over 2. And the tangent, remember, takes the y value and divides by the x value. So if I wanted to take my y value, divide it by my x value, I'm going to get 1 over radical 3. And that can be rationalized. Oh, my nose is so itchy. But I'm going to leave that just for a second. Okay, then I have my 45-degree angle, which we said is going to intersect the unit circle at radical 2 over 2 and radical 2 over 2. So that tangent's going to be nice. If I divide that y value by that x value, dividing something by itself, dividing anything by itself is going to end up just giving us a 1. Okay, maybe I'll just rationalize this. This is going to end up being radical 3 over 3. I don't know why I didn't do that. Just took 10 seconds. Not even 1 second, a tenth of a second. Okay, so let's finish simplifying over here. Tangent of 45, just said that's going to be 1. We're going to subtract the tangent of 30, which we calculated would be a radical 3 over 3. And then over, we have 1 plus the tangent of 45, which was 1, is going to be multiplied by the tangent of 30, which was radical 3. Okay, so we're looking at 1 minus radical 3 over 3 in the numerator of this complex fraction, and 1 plus radical 3 over 3 in the denominator of this complex fraction. We do not want to leave these fractions within the fraction. So the trig part of our work is done. It's going to be algebra work from here. And actually, let me rewrite this. Remember, to simplify the complex fraction, if we can get common denominators for everything, then we can get those denominators to go away. So what I would do is multiply by 3 over 3 here, multiply by 3 over 3 here, and now all of our fractions have denominators of 3. So ultimately I can put those fractions together and rewrite my division problem as a multiply problem, and again those common denominators are going to cross reduce. So I'm going to end with just my numerators, which would be 3 minus radical 3 in the top, and then we're looking at, I need another color here, 3 plus the radical 3 in the bottom. I don't know why I changed that. So 3 plus radical 3 in the bottom. And I don't know, I'm pretty okay with this answer. However, if you remember back to your algebra days, not only is it not proper to leave fractions in a fraction, it's also not really proper to leave irrational numbers in the bottom of the fraction, like that 3 plus radical 3. So this is technically something we should rationalize. In the same way we wanted to rationalize this, we should rationalize this binomial denominator. And I'm going to really run out of space here. I should have budgeted a little bit better. So to rationalize a binomial denominator, we multiply by the conjugate. So the conjugate of the denominator, which should be 3 minus radical 3 on the top and the bottom. So that's going to get me, oh my gosh, not enough. Let me move this. Not enough space. Note to self for when I do this in class tomorrow. Okay, so on the top of my fraction, 3 times 3 is going to be 9. Then I'm going to have negative 3 radical 3, another negative 3 radical 3, which would be negative 6 radical 3. And then negative radical 3 times negative radical 3 makes a positive radical 9, which is just going to be 3. On the bottom of the fraction, since I'm multiplying conjugates, I'm going to end up with the difference of squares. The middle terms will cancel. So I just need the first product, which is 9, and the last product, which is a negative radical 9 or negative 3. So then 9 plus the 3 is going to make 12, and then I still have that minus 6 radical 3. In the bottom, 9 minus 3 makes 6, and now I can reduce all 3 of the terms in the fraction. The 1, 2, 3 terms all have a 6 in common, so I'm going to divide everything by 6 and make the final answer, that's my highlighter, make the final answer 2 minus 1 radical 3. And there it is. So we're going to say, finally, that the tangent for 15 degrees is exactly 2 minus radical 3. And that was a lot of work. Maybe I spaced it out. Maybe I showed more work than is necessary. But hopefully I didn't lose you in the algebra. That's supposed to be the old part. Now, because we did so much work, probably a good idea to verify. Let's go ahead and calculate the tangent of 15 and make sure that ends up being the same as 2 minus radical 3. And yeah, we're good. Alright, one more here going in reverse. So when you see this, it should be looking like one of our formulas. It looks like, again, sorry for the page flipping here, but it looks like this formula here. We have, or this part is the part we're looking at. We have sine, cosine, cosine, sine. We got that minus in the middle, which means it's going to be the sine of the difference. So back here, I can rewrite this. Maybe I'll just put the formula for you here. So we have the sine of u minus v equal to sine u, oh my neck, sine u cosine v, and then minus cosine u sine v. Exactly what we see here, but it's giving us u and v, and it's all expanded. We're just going to put it back together. So in our version, the 80 is going to be u, and the 20 is going to be v. And here it is again, u and v. So we're going to condense this and call it the sine of 80 minus 20. And 80 minus 20 is 60, so we're really just looking for the sine of 60 degrees. Now remember, our 60-degree angle intersects the unit circle at 1 over 2 and radical 3 over 2, and that is the sine for that angle. So our answer is going to be exactly radical 3 over 2. So we can use the identities in both directions. We're not going to see it as often expanded out, but again, we've extended our ability to find exact values for angles that aren't explicitly on the unit circle. Alright, so these identities not only can they be used to evaluate, they can also be used to verify. So we're going to try that in the next two problems. So use a difference identity to verify that the sine of pi over 2 minus x is equal to cosine. This is actually one of our cofunction identities that we just talked about a few minutes ago. So I already verified graphically that if you reflect over the x-axis and translate pi over 2, that sine maps right onto cosine. So we saw that this is true. We already called this an identity, but now we're going to use our difference identity to verify. So the difference identity, sine of u minus v, that formula says that we're going to take the sine of pi over 2 multiplied by the cosine of x, and then we're going to subtract the cosine of pi over 2 and multiply by the sine of x. So that's just the sine of our difference identity formula. And pi over 2, remember that's 90 degrees. That intersects the unit circle. That's on the positive part of the y-axis, so we go just up 1 unit. So if I wanted the sine of pi over 2 right there, that's just a positive 1. So that's going to be 1 multiplied by the cosine of x, which is going to have to stay cosine of x because I don't have the value for that variable, minus the cosine for pi over 2 is 0, and that's going to be multiplied by the sine of x. Well, multiplying by 0 means that's going to cancel. So I'm just left with 1 times the cosine of x, which is the cosine of x. So we have verified using our difference identity one of our cofunction identities. Kind of cool in a nerdy, if you like math kind of way. Alright, let's try another one. This one looks much worse. Remember, when you're trying to verify, pick the side that looks like we can break down a little more, that looks a little more complicated. So I have the sine of a sum. So this first part here, I'm going to use my sine of a sum formula. So that's going to be the sine of pi over 6 cosine of theta, and then plus cosine of pi over 6 sine of theta. And then over here, I'm going to use my cosine of a sum formula. So I'm going to be adding my cosine sum formula says take the cosine of pi over 3 and then the cosine of theta. And then we're going to flip the sign on this one, so subtract is going to be sine of pi over 3 and sine of theta. Alright, it's a big mess. So pi over 6, 1/6 of the pi, that's 30 degrees. Pi over 3, that's 2/6 of the pi. So that's going to be our 60 degrees. So 30 degrees intersects the unit circle at radical 3 over 2 and 1 over 2. 60 degrees intersects the unit circle at 1 over 2. Oh no, come on, pen. You're doing great. 1 over 2, radical 3 over 2. Okay, so when I ask for the sine of pi over 6, right there, it's a half. And the cosine of theta is going to stay in there, so don't know that variable. Cosine of pi over 6, right there, radical 3 over 2. And sine of theta, again, that's going to stay. Plus, on the other side over here, cosine of pi over 3, or 60 degrees, cosine right there, that's going to be a half. And then cosine of theta is going to stay. Minus the sine at pi over 3 is radical 3 over 2. And that's multiplied by the sine of theta. And now we have some like terms we can combine here. If I have a positive radical 3 over 2 times sine of theta and a negative radical 3 over 2 times sine theta, those two terms are going to cancel. I can also combine a half of a cosine plus another half of a cosine, a half and a half, making one whole cosine. So cosine of theta, and we did it. We have verified that what we have here is what we have here. Okay? So we can use these identities to evaluate. You can also use them to verify. This one was cooler, number 5, because it's one of the identities we saw earlier, but also kind of fun. Just make sure you're being really careful about your formulas. Alright, last little thing we're going to see is using our identities to rewrite functions if possible. So here, for example, use an identity to rewrite the function as an expression involving functions of theta. So let's just use our identity to expand this out. Again, this is the sine of a difference. So the sine of a difference says, take the sine of the first one, so sine of 30, and then it's cosine of theta, and then we're going to subtract cosine of 30 sine of theta. And 30 degrees, for like the 18th time, intersects the unit circle at radical 3 over 2 and 1 over 2. So the sine for 30 degrees is a half, and that's being multiplied by cosine of theta. This is an equal. That looks terrible. That's an equal. And then cosine for 30 degrees, that's radical 3 over 2 multiplied by the sine of theta. And then I don't know if there's much more we can do with this. Maybe factor. Both of these have a 1/2 in common, so if I factor out the 1/2, then I have left a cosine theta minus radical 3 times the sine of theta. And that's really it. Can't really do anything else to simplify this, but this would be a function. So it says rewrite this as an expression that involves functions of theta. Well, sine and cosine are both functions of theta, so we've done it. We could say that the sine of 30 minus theta is equal to 1/2 times the cosine of theta minus radical 3 sine of theta. Super fun, right? Just a process of manipulating and using a little bit of algebra and the factoring, but really not bad. Let's try that one more time. So tangent 1, we have the tangent of a difference. So the tangent of a difference formula says take the tangent of u, which is theta in this case, and subtract the tangent of v, which is 3 pi in this case, divided by 1 plus tangent of u, tangent of v. And then let's see how much we can do. So 3 pi, gotta know where that's at. Probably easiest just to look at the unit circle. 3 pi, so we know that 2 pi is 1 lap all the way around, right? So this is 1 pi, this is 2 pi, then 3 pi would be another half of the loop. So 3 pi is really the same as 1 pi. They're coterminal angles. That's 180 degrees. So here, let's say, oops, highlighter's still on. That 3 pi is coterminal to, or has the same, let's say reference angle, but we're on the negative part of the x-axis. So 3 pi intersects the unit circle at the same place pi does, and that is at -1, 0. Okay, so let me try to simplify here. Tangent of theta is going to stay in there because it's got a variable. We're going to subtract the tangent of 3 pi. So tangent says take the y value, divide by the x value. Well, 0 divided by -1 is just going to be 0. And then on the bottom, I have 1 plus the tangent of theta times, again, tangent of 3 pi is going to be 0. It's going to make this part of our fraction go away. So we're looking at tangent of theta minus 0 is just tangent of theta in the numerator. And then if I just have a 1 in the denominator, then I don't need all that. So this whole thing really just simplifies down to a tangent of theta. So the tangent of theta minus 3 pi is the same as the tangent of theta. So if I was to shift my tangent function by a factor of 3 pi, it's going to be the exact same function that we started with. Let me just verify that for you here so you can see graphically what's happening. So turn that one off, and tangent. So tangent looks like this. If I took tangent and, tangent, turn it on, and I'm in degrees. Well, I'm like, why does that look weird? So there's my tangent function. If I took my tangent function and moved it over 3 pi, it didn't do anything. It's the same exact function. Okay, because the period is pi, so at all those multiples of pi, we're going to see the same behavior. So if I shift it over a pi or 2 pi or 3 pi, I'm going to see the same thing. Alright, hopefully that makes a little bit of sense, and that's it. And hopefully you have enough, you've heard enough, and you're ready to go on to your homework. As always, if you have any questions, reach out. Until next time, take care.